Welcome to this explainer. Today, we're going to break down the fundamental physics that literally keep our world balanced, starting from everyday observations and scaling all the way up to extreme orbital mechanics.
Have you ever wondered why you can perfectly balance a pencil on your finger? Or why a towering skyscraper doesn't just topple over when the wind blows? Or maybe you've noticed how gymnasts contort their bodies mid-air to pull off those crazy flips. The secret to all these amazing balancing acts comes down to two absolute game changers in physics: center of mass and center of gravity. Now, a lot of folks think these are just two names for the exact same thing, but spoiler alert, they aren't.
Here's what we're covering today. First, the balancing act. Second, center of mass explained. Third, calculating the balance point. Fourth, enter center of gravity. And finally, are they the same? By the end of this explainer, I promise you are never going to confuse the two again.
All right, let's jump into part one, the balancing act.
Picture a cricket bat. It's all made of wood, right? But the handle is pretty light, while the bottom part is thick and heavy. If you want to balance it on one finger, you can't just hold it dead in the middle. You got to slide your finger down towards that heavy end. Well, there is one exact, specific geometric spot where you can hold it to balance it perfectly. Physicists call this the center of mass. It's basically this theoretical point where the entire mass of the object appears to be concentrated for the purpose of studying how it moves.
Moving right along to part two, center of mass explained.
Now, it gets really cool when things start moving. If you chuck a hammer through the air, it looks like this crazy, chaotic mess of spinning wood and metal. But look closely at that dashed line. That line is tracking the center of mass. So even while the hammer is frantically flipping around, its center of mass traces a perfectly smooth, predictable parabola, exactly as if you just threw a tiny single pebble. So, what are the actual rules here? Well, the center of mass depends purely on how the mass is distributed. And here is the kicker: it is completely independent of gravity. Seriously, it is a pure geometry and mass thing. That means this exact same balance point exists, whether you're standing here on Earth or floating in the near-zero gravity of deep space. Oh, and it doesn't even have to be located on the physical material of the object itself. This flying ring is the perfect example of that mind-bending fact. For shapes like a hollow ring or a boomerang, the center of mass actually sits in the empty space right in the middle. There is literally no physical material there, but if you toss it in the air, that empty geometric point is exactly what the object will smoothly rotate around.
Section 3, calculating the balance point.
Let's figure out how to actually calculate this point, starting simple. Imagine two particles, like two weights connected by an invisible, massless rod. Finding their center of mass is kind of like calculating your GPA. It's just a mass-weighted average of their positions. If one mass is a lot heavier than the other, it pulls the balance point closer to itself. You literally just multiply each mass by its position, add them up, and divide by the total mass. Simple math. But what if we aren't just looking at discrete point masses? What if you have a solid, continuous object, like a block of wood or an airplane wing? For separate particles, simple addition works fine, using the sigma formula you might remember from math class. But for continuous objects, engineers have to break out the calculus. They use continuous integrals to sum up an infinite number of incredibly tiny mass bits across the entire volume of the solid shape.
Okay, but let's say you really don't want to do calculus. You are in luck. There's a brilliant physical trick you can use to find the center of mass for any weird, irregular shape, and NASA even recommends it. It's called the plumb line method. Just hang the object freely from any single point. Drop a weighted string, a plumb line, from that exact same point and draw a line down the object tracing that string. Then hang it from a totally different point and do it again. Where those two lines cross, boom, that is your center of mass.
You can see it happening right here. Notice how gravity naturally pulls on the center of mass to bring it to its lowest possible point, right beneath the pivot. That absolutely guarantees the balance point lives somewhere along that vertical drop line. By doing it twice from two different angles, that intersection gives you the exact 2D coordinate without writing a single equation.
All right, part 4, enter center of gravity. So far, we've only been talking about mass, but, we live on Earth, which means gravity is always pulling down on us. Enter the center of gravity. By definition, this is the specific point through which the downward gravitational force acts on an object. If you've ever held your breath watching a tightrope walker wobble side to side to keep from falling, you are watching the center of gravity in action. It dictates how stable an object is and whether it's going to rotate right over. A super fun way to visualize this stability is with one of those classic Weeble toys. Things with a super low center of gravity, like this toy, or high-speed racing cars hugging the track, are incredibly stable. Why? Because their heavy base means that if you try to tip them over, you are actually forcing their center of gravity upwards. And since gravity always wants to drag things back down to their lowest possible point, it just yanks the object right back upright.
Which brings us to our final section. Are they the same?
Let's look at them side by side because they are definitively not the same. Center of mass depends purely on mass, exists out in deep space, doesn't care about gravity fields, and is used to figure out how objects move. Center of gravity? That's all about weight and gravity. It absolutely needs a gravitational field to even exist. It changes if the gravity field changes, and it's what engineers use to make sure buildings don't collapse. They operate by entirely different physical rules.
So why on earth do we constantly mix them up? Well, it's because for almost everything we interact with every single day, they happen to be in the exact same spot. If you're in a uniform gravitational field, like sitting right here on the surface of the Earth, gravity pulls evenly on every single part of a small object like your school bag. Because that pull is completely uniform, the geometric center of mass and the gravitational center of gravity perfectly line up at the exact same location.
But wait, what if we go big? Like impossibly big? What if you have a massive structure and the gravitational field isn't uniform? Remember, gravity gets slightly weaker the further away from the Earth you go. So for a ridiculously tall structure, gravity actually pulls harder on the foundation at the bottom than it does on the peak at the top. Because the bottom is being pulled stronger, the center of gravity physically shifts downward, pulling slightly lower than the actual geometric center of mass.
And this distinction is an absolute game changer in astrophysics. Think about two massive planetary bodies orbiting each other, like Pluto and its moon Charon. Because of how gravity and mass interact on that kind of epic scale, their shared center of mass, called the barycenter, can actually sit right out in the empty void of space between them. It acts as an invisible pivot point that both worlds just dance around. So, we've gone all the way from balancing a tiny pencil on your finger to the orbital mechanics of moons in deep space. I want to leave you with this to think about. If you were an engineer and you had to build a skyscraper so incredibly tall that the top felt noticeably less gravity than the foundation, how would you design it? How would you outsmart nature if the center of mass and center of gravity of your own creation decided to split apart? Thanks for checking out this explainer, and keep questioning the balance of the world around you.